lot of times when we're looking at radar on our apps, it's just looking at reflectivity mode, which is just what we could see with precipitation. But we can look at radar behind the scenes too to see inside thunderstorms as to how they're rotating and the speed that they're moving at to detect where tornadoes are or where damaging winds are within thunderstorms. So we've gone over the basic aspects of radar, how they send out radio frequency energy, and that's received back by the radar once it bounces off of precipitation. You might have heard of the Doppler effect. That's going to be one of the kind of core concepts for how the radar detects the speed and direction of precipitation. Now, the Doppler effect works when you have some kind of moving object coming towards an observer. When it's coming towards you, you have a higher frequency. When it's going away from you, you have a lower frequency. And the person that discovered this was Christian Doppler. That's who it's named after, back in 1842, an Austrian physicist. And here's an example. You might have most commonly heard this related to a car horn or just a loud engine moving past you. Here's an example of how the Doppler effect works in the real world. So similar to how the car is moving away from you and having that lower pitch, we can change the frequencies or the wavelengths of the energy that is being emitted from radar. Remember, the radar is emitting that radio frequency energy, so these wavelengths can be compressed when the rain or the objects are moving away from the radar, and when they're moving towards the radar, they're more compressed. When they're moving away from the radar, the frequencies are a lot longer. So similar to that Doppler effect, you have the radio frequency energy going out to thunderstorms, being bounced off of that. When the storm is moving towards the radar, that energy gets more compressed. The wavelengths get pushed together more. You have a higher frequency, and the radar can detect that. When the storm is moving away from the radar, those frequencies are farther apart from each other. So here's another kind of schematic of that. It's precipitation moving away from the radar site. Your frequencies that are coming back, those red lines, are farther apart from each other, versus when the precipitation is coming towards the radar site. The frequencies, the green lines in this example, are a lot closer to each other. And that's very important and powerful information when we're looking inside of thunderstorms. So this is that basic reflectivity mode that's telling us how heavy it's raining out. But with this kind of hook echo shape, we can usually tell that that's a tornado. But looking inside the storm with that velocity data, we can see the greens indicating the precipitation going towards the radar, the reds moving away from the radar. So you can see that rotation within the storm. A little bit of a more subtle example, when you don't have that kind of hook echo on your reflectivity mode, we could also see the winds moving towards and away from the radar site, and that can detect where rotation is, and we can call that a velocity couplet. Velocity couplets are what meteorologists use to issue tornado warnings by just looking at this velocity data and other products, but this velocity data is really one of the most important things to see inside the storm, see that there's really tight rotation and strong rotation, because we can tell how fast those particles are moving right next to one another, and then issue a tornado warning. Here's one example from North Dakota back in 2010 in Burke County with this tornado, a real-life image of it. But on radar, we could see that rotation with the bright greens and the bright reds right next to one another, indicating that rotation within a storm. So how does this information get utilized for meteorologists to issue tornado warnings? Here is Chauncey Schultz explaining more about that.
So when we say that there is a radar-indicated tornado, what we're really sensing is that there's strong rotation in the clouds right near the ground. We can't, most of the time, positively say that there is for sure a tornado. But what we can sense is that there is really strong rotation a few thousand feet above the ground, or as close to the ground as we can get with the radar. And that very often is a tell that a tornado is going to form soon. So we're trying to gain lead time, advanced warning on the tornado genesis is what we would call it. And we can do that by sensing inside the clouds, seeing which direction those motions are within the clouds. If they're rotating very quickly, then we can issue a tornado warning that is radar indicated that a tornado could form at any time.
And it's not just with tornadoes. With how fast the winds are moving within a storm, we could see that there's a very strong downdraft or something that's going to produce damaging winds when we look at that velocity data.
It's kind of like detective work you're doing there.
Yeah, basically, we could see kind of a scope inside the storm where you can't really see that from just outside.
Yeah.
These radio frequencies are amazing, and it's helped us as meteorologists along over the decades, really pinpointing the severity of storms, and tornado detection. So it's just fascinating.
Before you had radar, what did you do to? Well, you don't remember that, but I mean,
Yeah.
what did weather meteorologists do?
The tornado detection has improved greatly since we've gotten this Doppler technology within the past 30 years. And with that Doppler technology, our tornado lead times have improved. So before that, we couldn't really assess where exactly tornadoes were before. It was a lot more challenging.
You guys do a good job of warning us.